My name is Jeremy Schwend, and I'll be speaking about surfaces with vanishing curvature, focusing on the convolution case. Consider a manifold in Rn with some surface measure mu. Many questions in harmonic analysis relate to the curvature of that manifold. For instance, convolution, LP or Sobolev bounds, Fourier restriction operator, or maximal operators. In each of these cases, techniques and results tend to be simpler when curvature is non-vanishing, though many of them can still be quite difficult. So what happens with these operators when the curvature vanishes? Well, nothing good. You get less Sobolev or LP smoothing for convolution, worse restriction estimates, and sometimes restriction doesn't even make sense, and similarly with maximal operators. In this topic, I want to focus on LP smoothing and the convolution operator, though some comments will be made about restriction. So, let's look at the broader picture first. Suppose we have an operator tied to convolution with a measure mu supported on a manifold. For what P and Q do we get LP boundedness? Well, if this manifold is a curve, a lot is understood. Whereas with intermediate codimension, there's a lot that is not understood, though progress is currently being made, a lot of it. And an intermediate case would be the hypersurface case. Hypersurfaces are well studied, but there are a lot of open questions. So today I'm going to focus on hypersurfaces. If curvature is non-vanishing, there's a lot that is known, but many unknowns remain when curvature is allowed to vanish. So, how do we quantify the effect of vanishing curvature? Well, there are two primary ways. We can look at the change of the bounds or the LPOQ region, or we can try changing the measure. Let's start with the measure. The affine surface measure is when we weigh bad regions less, regions with vanishing curvature less, to recover uniform estimates. The benefit of this is we get simpler to state results, but a downside is the measure is non-Euclidean. The measure vanishes when curvature vanishes. Alternatively, we could try using the Euclidean surface measure or something comparable. But a downside is the results tend to be complicated to state. A related question would be, can you go back and forth between these two? And how so? How do they relate? So let's first look at the affine surface measure that weighs bad regions less. So with convolution, we have this wonderful result for Oberlin and Gressman, where phi is allowed to be a polynomial. And if we look at what's going on here, what's happening is f is being convolved with a surface measure on the graph of phi. And this determinant of the Hessian is our affine surface measure weight that vanishes when the curvature vanishes. One thing to note is that we get nice uniform results at a single point with a very uniform bound depending only on the dimension and the degree of our polynomial. So, what happens if we jump over to the Euclidean surface measure? Well, first off, I'm going to narrow our focus to R3, an actual surface in R3. And I'm going to narrow further to mixed homogeneous polynomials. If kappa 1 equals kappa 2, this is just standard homogeneity. But we are allowing kappa 1 and kappa 2 to differ. Mixed homogeneous polynomials act as scaling limits for general polynomials, and in fact, they are great stepping stones going towards a general polynomial theorem. Many of the effects one would see in the general case start appeaing in the mixed homogeneous case. So here is our theorem tied to mixed homogeneous polynomials. We're in R3, and note here that there is no weight, but we've also narrowed ourselves down to a compact region. But we get precise restricted weak type bounds, and I'll explain restricted weak type in a bit, if we satisfy certain complicated conditions. Now, what are those complicated conditions? Well, as you can see, this is a lot more complicated than the Oberlin-Grassmann result. And if we want to look at what goes into these quantities, we get something like this. I won't spend any time on this page, but let's suffice it to say that you can phrase these complicated conditions in terms of the factorization of phi and its derivatives. So first off, I wanted to mention a little bit about restricted weak type bounds. So first off, standard LPOQ bounds in their dual form can be phrased as a bound in terms of the norms of f and g. With restricted weak type bounds, the only difference is we restrict ourselves to characteristic functions. That causes restricted weak type bounds to be weaker by a bit, but only at vertices. Interpolation causes all interior results to be equivalent. So that only weakens vertex results. Now, let's look at the prior results on this problem. So in 98, there were results for additive functions, and these results covered all dimensions, not just R3. In 99, convex surfaces. In 06, complete results for homogeneous phi. In 17, results for mixed homogeneous polynomials. And right now I'm going to introduce two cases, but we're going to leave them as black boxes for the moment. The rectangular case, they achieved complete interior results, but the boundary was left unknown. And in the twisted case, there a region remained between conjecture and theorem. So, let's look at the Riesz diagram. How does the affine and Euclidean results compare? Well, here is what the region of boundedness looks like for the affine measure. This 3/4, 1/4, that is the Oberlin-Grassmann point in R3. I've also put this other point, 2/3, 1/3, the R2 result of Oberlin-Grassmann in as well. The Euclidean measure result is this green region. And I'll show you a few examples, depending on the phi you're using. So, how do we begin? Well, we start by decomposing our surface into dyadic pieces, as follows. First, we finitely decompose around the zeros of the curvature. We look at where the curvature, the Hessian, vanishes, and those affine curves, and we look at neighborhoods of those regions. And then we do a change of variables. We want to take those affine curves and line them up with an axis. So we do a change of variables to do that. And then we dyadically decompose based on the size of the curvature, and we further dyadically decompose into rectangles in these new coordinates. And then we look at the individual dyadic regions. And when we do so, two cases arise. And here we're going to explain those black boxes. The rectangular case, in this case, those pieces look morally like paraboloids. or hyperbolic paraboloids. So we can compare estimates on paraboloids to the estimates on these pieces. But sometimes that estimate doesn't work out. Sometimes these regions have not quite a helix structure, but still some sort of twisted structure like helix would have. And so the estimate of comparing it to paraboloids is a bad estimate. And we can do better. So let's first look at this rectangular case, the simpler one. So here there are three estimates that we focus on to begin with. First off, the kind of base estimates, L infinity infinity, L1 1. These are just the size of our measure, the size of the rectangle, the orbital region. Then there's the 4/3 bound that comes straight from curvature, the orbital and Gressman result, the Afferent result. And then the 3/2 3. This is the lower dimensional result where we're using lower dimensional curvature information. So to achieve that, we have to slice and use lower dimensional estimates. So we take all of these estimates and interpolate and optimize. And that does give us optimal estimates on these dyadic pieces, which simple summing would give bounds in the interior of our region. And to achieve endpoint estimates, we sometimes need to use orthogonalization techniques. So, first off, in the rectangular case, there are two relevant vertices where we have to prove boundedness, V1 and V2. And there are two big challenges that arise here. Challenge one, sometimes complications occur with V1. Namely, in these bad cases, the size of our rectangular regions, the L infinity infinity bounds, end up gaining a logarithmic term. And that logarithmic term destroys our interpolation. So we have to fix that. And the second complication comes with the 2/3 1/3 bound. In some of the harder cases, extra effort is required. So let's start with the vertex 1 issues. So first off, the restricted weak type bound, 4/3 4, can be rewritten in this dual form. So if we're only doing convolution with a single piece of the surface, then if this term is large, that ends up implying that E and F have to be highly aligned with the surface. But that allows us to exploit and use an orthogonality argument. If this is large, then E and F are highly aligned with the surface, which means that distant pieces, by orthogonality, will achieve small results at 4/3 4. So we can actually sum those up and achieve our desired result. And this uses a variant of Chris' method of refinement. So let's go into this method of refinements. So we can rephrase the 4/3 4 restricted weak type bound in this dual form. Now, if we rewrite this and rearrange it, here's a rearrangement, and then let's simplify again. And we've now rearranged this restricted weak type bound in terms of averages. Now, we can also phrase this in terms of incidences. What do I mean by incidences? So let's assume we take our surface, the origin of our surface, and move it to a point in E. Then, on average, about alpha of our surface will intersect F. Similarly, if we mirror our surface and move it into F, the intersection with E would be approximately beta. So we refine E and F to take these incidences and turn them into lower bounds. And then we use a TT star method to create a map to exploit and analyze these incidences. So, to create this map, we start from F, go to E, and then go back to F. And we're using two copies. So notice there's one T but two S's. A part of the reason we're using two copies is because of this F squared. But another reason is we need this map. For this map, we need the dimensions to match, R6 to R6. But now, by analyzing this map, we can analyze and exploit this incidence information. So we actually look at the average of the Jacobian of this map. And by properly bounding it, the Jacobian, we achieve our goal. Now let's talk about the orthogonality argument we need to use to fix the issues in the vertex 1 bad cases. So the orthogonality arguments. So suppose we have two pieces of our region, and we're only going to focus on pieces where the curvature is approximately 1. And this introduces averaging operators. So suppose those pieces achieve the maximum possible 4/3 bounds. Assume that both of those are large for a set E and F with 4/3. We want to show that if they are large, those pieces of the surface have to be close together. An orthogonality argument. So we refine E and F separately. And under this assumption, one can show that EK intersect EL will be large, and similarly with F. So we use that as a bridge in our map we created before. So we first start with FK. We're starting with the K piece of our surface. Then we go to the intersection and find ourselves in the L piece of the surface. So as before, we can use this bound, but what we find is that if the pieces of our surface are far apart, then the effect of orthogonality leads to a contradiction. So now I want to turn to the 3/2 case. So we're again going to use the method of refinements. So we can rewrite the restricted weak type 3/3 bound in this dual form. And if we rearrange it in terms of incidences, we get F is greater than or tilde to alpha squared beta. So let's try building our map in a similar fashion. We refine E and F and create a map from R4 to R3, like so. However, there are two problems. One, we haven't really done slicing to reduce the dimension yet. We're supposed to be looking at lower dimensional curvature information. But two, the dimensions don't match. So to fix both of those issues, we freeze one of the coordinates of t and use some sort of pigeonhole argument to justify. And that causes the dimensions to match, but it comes at a price. The price is the Jacobian of this map loses a lot of its symmetry. And how does that play out? Well, the loss of symmetry forces one to use approximation techniques. So, for example, to fix this loss of symmetry, I used the mean value theorem. And in these mixed homogeneous cases, the mean value theorem was able to resolve all of the issues. However, I'll mention later some other issues that might arise. But that is an issue, that the Jacobian has far less symmetry, though it's not really a problem in this mixed homogeneous case. Now let's turn to the twisted case. So in the twisted case, approximating with paraboloids is non-optimal, and we can actually do better. So first off, in this case, we only have two relevant estimates. The base estimates tied to the size of our region, and the curvature information estimates. We actually avoid needing the lower dimensional curvature information. A problem in this case, what problem arises with the twisted case is that both of these cannot be large at the same time. And that causes interpolation to not be optimal. So the idea is we quantify this trade-off using the geometric information to get new optimal LP/LQ estimates. So let's look at the Riesz diagram. In this case, we just have a single vertex, V1. So our strategy is we divide this twisted region, and the region would look more like what's on the right. We divide this twisted region into smaller strips that actually are well approximated by paraboloids. And the intuition behind this is if the 4/3 form effects are large for a specific region, then that means that E and F had to be well adapted to a single strip. And that causes this to be small if we look at other strips. And because of that, this causes the L11, L infinity, infinity bounds to also be small. So you get this trade-off. If 4/3 4 is large, L11 is small, that we need to quantify. So to do this, we once again turn to the idea of the method of refinements. But before that, consider, let tau KL be a small subset of our surface. And we project that down to R2, so it's a two-dimensional. It's living in R2, with tau being the associated operator. Now we look at what the gradient does to this piece of R2. In our rectangular cases, this piece under the gradient would look like the neighborhood of a line, nearly convex. But in the twisted case, it's far from convex, looking more like the neighborhood of a parabola. However, even with a parabola, you can still break a parabola into small caps that are approximated by tubes. And these tube-like, nearly convex caps actually relate to our smaller strips from the previous slide. So, the idea is if the 4/3 4 effects are large, then the contributions are coming from a single cap. And that means that the L11 effects are small. So, suppose multiple caps were contributing. What happens is, if we analyze this with the method of refinements, to look at the 4/3 bound, the Jacobian of that map, if one looks at the method of refinements, this Jacobian is actually proportional to the area of the convex hull of regions. Whereas the L infinity bounds are proportional to the area of the caps, the regions themselves. So in the rectangular case, the area of the region and the convex hull are proportional. Whereas in the twisted case, these are not proportional. And that is what allows us to quantify the trade-off. So now I want to discuss a little bit about the general case and what new things arise there. So, in the general case, with general polynomials, two new complications arise. First off, I mentioned before the L3 halves L3 bound, and the issue with the loss of symmetry in Jacobian phi. In the mixed homogeneous case, this was very manageable. But it becomes harder to manage, much more problematic in the general case. Also, the twisted case. In the mixed homogeneous situation, the twisted case was able to completely avoid the lower dimensional curvature information. But in the general case, lower dimensional information is now required. Finally, to wrap up, I wanted to mention a little bit about Fourier restriction and also my joint work with Betsy Stovall. First off, Fourier restriction is more difficult than convolution with some of these matters. For instance, the affine measure results, which are fully fleshed out and nicely uniform in the convolution case, are very much still unknown in the Fourier restriction case. And one of the big problems with achieving nice affine measure results is the fact that with Fourier restriction, negative curvature is really hard to deal with. Convolution, negative curvature doesn't really affect anything, but Fourier restriction, it is hard to deal with. But in my joint work with Betsy Stovall, we looked at some of these issues tied to simpler cases in Fourier restriction by estimating the precise bounds of rectangular regions of surfaces. So I will end things there, and thank you very much.